Hi students, this is Miss Wendt, and this is the second part of the notes for Chapter 3, Section 2. In the first part that you should have seen, I talked about the greenhouse effect, and we wrote down 4 gases that cause it. And we learned that it's required for life on planet Earth. We do need this to trap some heat in, but too much could be a bad thing. Okay, so if you have not done the first part of the notes, please stop this video and go back and do those first. Okay, this video, I want to show you a video clip from YouTube to help explain it, and then go over the assignment you have on the greenhouse effect to make sure we're understanding what we're doing. Okay, so here is our video clip from YouTube.
The Earth and the Moon are basically the same distance from the Sun, yet temperatures on the Moon average an unlivable -18 degrees Celsius. And even deadlier, they range from -170 Celsius during lunar night to 100 Celsius at lunar noon, regularly exceeding both the coldest and hottest temperatures ever recorded on Earth.
Okay, just a quick reminder, this is Celsius. So 100 Celsius is where water boils. So if you're in the sun, it's as hot as boiling water, right?
And while the days and nights on the Moon are about 14 times longer than those on Earth, our planet's relatively fast rotation isn't what spares us from those loony temperatures. What protects us is our atmosphere. By day, it serves as a shield, blocking out the most harmful and energetic of the sun's rays and about 1/3 of the less intense but visible light.
Okay, so you can see here, this is blue lines representing our atmosphere. And you can see that some rays of sunshine are getting in, but a lot of them are getting blocked. Getting blocked up here also includes X-rays, gamma rays, most ultraviolet light. All of those energy rays can cause cancer in us. So that's a good thing. We've got to have that atmosphere, or living things wouldn't be here. Everything would just die of cancer. Okay, but some things do get through. Okay, so that's kind of what this diagram is showing. This is all the energy coming from the sun, a lot of it being blocked by the atmosphere, but a few things are getting through, mostly visible light and heat energy.
At the same time, it traps the infrared radiation, aka heat, radiating out from Earth's sun-warmed surface, keeping us from freezing solid at night. In order for our atmosphere to absorb any kind of radiation, it needs to have some electrically charged particles for passing electromagnetic waves to push around. And most of our atmosphere is made up of gas molecules that don't have an electric charge. They all have a balanced number of positive protons and negative electrons. But some molecules hold most of their negatively charged electrons closer to one side, lending them a lopsidedness that can jiggle back and forth to absorb the energy of incoming infrared rays. For example, water, ozone, and nitrous oxide are all electrically lopsided, so they all absorb infrared radiation. Then,
if I back up just a touch here, guys, you do not have to have this stuff memorized, but it is kind of a cool visual to think that, hey, when this gets hit with a little packet of energy from the sun, that energy makes it move, just kind of like if you get hit by a car or something, right? And if you think about like your muscles moving, that creates some heat energy. Well, this is kind of turning that visible light energy into heat energy. So it's the same energy, we're just changing it from one form to another. Some chemicals can do that really well, and some can't. You do not have to memorize which chemicals do which, okay? If you have the 4 from our notes, that's what we're going to worry about.
Radiation. Then there are gases like carbon dioxide and methane. On paper, neither molecule looks lopsided, so it doesn't seem like they should be able to absorb any radiating heat. But in reality, gas molecules aren't motionless. They crash into each other billions of times per second, knocking each other in different directions and also into different modes of rotation and vibration. And it turns out that both carbon dioxide and methane spend most of their time shaking it in electrically lopsided ways, allowing them to absorb infrared rays and help insulate the Earth. Even though many different kinds of molecules can absorb infrared radiation, the vast majority of our atmosphere can't, because it's made of nitrogen and oxygen, which don't get lopsided even when they are vibrating. They're too symmetric. Nevertheless, the lopsided 1% are such good infrared absorbers that they manage to intercept about 90% of Earth's outgoing heat. Each captured ray gets pinged around the atmosphere, and most end up returning to the surface at least once before escaping to space.
So what it was showing there is it's showing that little wave of heat energy, kind of it hits one of these gas molecules, these greenhouse gases, and gets bounced back down. But eventually it does escape. Okay. Now picture in your head, what if instead of 4 blocking molecules up here, I had 8 or 12? It would be a lot harder for that heat energy to actually leave, and the amount of heat would build up and up and up over a series of time.
We don't need to visit the moon during frigid lunar night to know just how important the game of radiation pinball is for Earth. Ice records from our own coldest climate show that small natural variations in atmospheric carbon dioxide produce relatively big changes in temperature. They also show that, compared to the last 800,000 years, the game today is much, much harder.
So you can see at the end of the video there was a lot more molecules blocking, and that made things a lot more complicated to try to get that heat energy to leave. Okay, so we're going to do a simulation so you kind of can see this in action. So in Schoology, you're going to have an assignment that's Explore Learning, Gizmo, the Greenhouse Effect. And the first couple of questions here are just kind of brain warm-ups. You don't need the simulation to do these. Okay, vocab words here, we've talked about these guys. Global warming is the idea that the Earth is getting warmer and warmer and warmer over time because of the buildup of these extra greenhouse gases. The greenhouse effect helps keep heat in planet Earth. It's a good thing as long as it doesn't get out of control, and it's getting out of control right now. Greenhouse gas, we wrote 4 of those in your notes on the previous video. And then heat flow is just the heat energy moving from one place to another. So from the sun to the earth to the air, back down to the earth, how is the heat moving? So those words might be useful as you're answering questions. So prior knowledge questions here. Number 1, what do you notice when you get in a car that's been sitting in the sun for a while? Okay, well, I would maybe write down, it is hot, right? Like my son will complain that his seatbelt is too hot and he can't buckle it. Things like that, right? So if in the summertime, if the car's been sitting in the hot sun, it gets really hot inside. But why is it so hot? I mean, it's sitting in this, it's getting the same amount of sun as the air outside the car. Why can the car get 100 degrees hotter than just the air outside? And the reason is the car traps heat. Okay, so what that means, let me try to make this a little neater here. So the car is going to trap heat. So light goes into the windows. Okay, so the light energy gets in the windows, but then lose a bit of energy, and the heat cannot get back out of the windows. Okay, so when that light goes into the window and hits the seat belt or the car seat or the dashboard or the steering wheel, when the light hits that, it loses a little bit of energy, and then it doesn't have enough energy to go back out the glass. I mean, some of it might, but a lot of it gets trapped. And that trapped heat builds up and builds up and builds up, and pretty soon the temperature inside the car can get dangerously hot. It's so important to make sure that you never leave young children or pets inside a car, because this effect can happen within just a couple minutes. Okay, so number 3, I'm going to leave that one for you. How would things be different if the car windows were left open? Okay, so what difference would the car windows make? So you can go ahead and pause the video, make sure, get this worksheet out of Schoology if you need to. Answer these first 3 questions, and then come on back to the video. Okay, so you should have the top of the worksheet done, questions 1, 2, and 3. Now we need to go to the website explorelearning.com and get logged in. And there was a video that kind of shows you how to do that, so hopefully you've done that. So here's explorelearning.com. Username and password, it's probably the same as what you use for Schoology. If you don't know how to get in here, please look at the directions, watch the video, see what happens. Okay. And you will have this set up on your screen already. I just haven't done it for you yet. I made the video first. So when you log in, you should see this gizmo called greenhouse effect. Okay. And there's a couple things you're able to move. You are able to change how many of those gases are present. So look, the carbon dioxide, the methane, and you're able to crank the speed of the simulation up to make things go faster if you wish. Okay. On this side over here, you have a data table that will collect data. So how much heat is going in, how much heat is coming back out, and what the temperature inside the box is. Bar chart, so you can kind of see things changing, going up and down. And you also have a graph. And remember, you can zoom in and out of the graph and drag the graph around if it goes out of view. Okay. So I'm just going to reset everything back to kind of where it started. If I hit play here, you can see there's nighttime, there's daytime, nighttime, daytime. So if I look at the bar chart, well, this kind of makes sense. Temperature goes down at night, goes back up during the day. You know, we see that happen in our own lives, right? It cools off at night, it warms up during the day. So you can see that when the sun comes up, we get lots of heat going into the system. As the sun sets, now there's no heat going into the system. But notice this purple bar. The amount of heat leaving stays the same. Okay, so the amount of heat going in depends on if it's daytime or nighttime, but the amount of heat leaving stays the same. So that's an observation we should make. With our graph here, you can see that the temperature in green goes up during the day, back down at night, up during the day, down at night. The heat going in kind of matches that. Sun goes up, sun goes down, and the heat going out is a flat line because it's staying the same. Okay, so this is just if everything stayed the same, normal. But that's not real life. In real life, humans are putting a lot more greenhouse gases in. So you're going to follow directions on your worksheet for different amounts, and you're going to see how these numbers change and see if things even out, if things keep going up forever, if things go up and crash back down, what happens. If you need a specific number for something, the data table, you can find that. Okay, so the time is in hours. So this is after 277.5 hours. So you could divide that by 24 hours in a day to find out how many days later that was if you need to. Okay, so we have a lot of data here. And it looks like the first part got erased, so the data table is only so big. So keep that in mind when you're doing stuff. You may have to set and restart a couple times, and that's fine. Okay. So the directions here say, click play, look at the bar chart and stuff, make some observations on the temperatures, and we just talked about that. And then later on, you will, make sure the greenhouse gas is at 10%. Write down what you see. Hit reset, change the amount of greenhouse gas. Which of these things do you think will change, and then what actually happened? So you're going to make it a hypothesis or a prediction. And it's okay if your prediction's wrong, nobody cares. And then you will actually do the experiment and try it and see if you were correct or not. Okay? There's a little description there, a little that you can do. Okay, so that is your assignment. I want you to use the simulation to answer the questions in your greenhouse gas assignment and hand it in. If you run into any trouble, please contact your instructor or a para. If you want to pair up with somebody over Zoom and kind of work on it together, that's okay by me. And so your job is to try to finish this assignment and hand it in. And again, if you have any questions anytime, you can always feel free to contact us. Thanks, guys. Have a great day.